Alrighty. So up until this point, the programs that you've been writing have not really had any real method of persistence to them, by which I mean that instead of using a real database, we've been writing to CSV files. So kind of faking our persistence up until this point. So this week, we're going to try to improve that. And instead, we're going to store our data using a relational database management system, which is also commonly known as a SQL-based database. Relational database management system, aka SQL database. So SQL is just a language. It's just the structured query language. And many different databases use this same language to interact with them. We call them all, SQL databases. In this cohort, in this program, the particular SQL database that we'll be using is Postgres, but there are a bunch of others. So let's see, I've used MySQL, MariaDB, Microsoft SQL, and then there's a whole bunch of other ones, but those are ones I've used, so I think they're pretty popular as far as SQL databases. But don't worry about all the different kinds of SQL databases because they're like 99% the same. So with the SQL knowledge that we give you in this course and the specifics you're going to learn about Postgres, you can transfer these skills over into any other SQL-based database that you might learn in your career. So before we just jump into how to use databases, I think it's important to pause and do some critical thinking and ask if we actually do need this new technology and if there isn't a simpler solution available. It's an important question you should always be asking yourself. And especially since we have the option of storing our data in CSV files, I want to spend a minute and explore situations where that will be insufficient. I'm going to explore some problems that are created with CSV files so we understand better the solutions that we're applying with databases. Porfi, question?
Yeah, just real quick, so before we get too far from it, what does persistence mean in this context?
Persistent being kind of the opposite of ephemeral, like it doesn't disappear randomly, but it'll stay, like you can store it securely.
Got it, thank you.
Yep. So I'll just define that real quick.
Can't sometimes persistence also be like, it's like a temporary intermediary between, like, say if you have like a cloud solution, you can have like a way to persist the data locally on your device in order to make your updates. That way you're seeing the feedback on your device from you engaging with the app, but it's not necessarily having to fully wait for it to go to an external server. You're persisting it locally on your machine or something like that.
Yeah. In that context, I'd say you're talking about persistence because normally the data would not be stored on your local machine at all. Maybe it would be like saved in
I think of mobile devices is what I'm thinking of more than anything.
Okay.
I think Firestore might do that automatically. I'm not sure.
So let's think back to our school database that we've been building, in a few different projects. Imagine we had a folder full of CSV files for different students. So imagine, I'm going to make just kind of an example folder hierarchy here. Imagine we've got a folder called data. Probably got some JSON files inside of it. So imagine we've got this folder full of JSON files. The name of each file is a student ID number. Now then, let's imagine that each of the individual JSON files looks something like this. Just going to grab this off the curriculum real quick. You don't need to watch me type out a JSON file. So this could be an example of student data stored in JSON, very common data format on the web. But as we'll see pretty soon, it's not the best format for this particular problem we're solving here. So everyone's data is pretty clearly accessible, first name, last name, classes, as all the classes they're enrolled in. There's a bunch of them, so we put that in a list, but it's all part of the student, so it's kind of nested under that same JSON structure. So depending on what we need to do with this data, it might be easy to interact with. So let me show you just an example of a program that you might use to query this data. Again, this isn't a super interesting program. I don't need you to watch me code it out. So I'm just going to paste this in here. So we've got something to talk about real quick. So here's a really simple kind of example program that could be used for querying data from our little CSV database I just showed you before. So we just get input from the user, which student ID are you looking for? You open up the corresponding data file that has that student ID as its name. And then we access the properties of this JSON file as a dictionary, just like you do with any Python dictionary, and print out the data. So here we're seeing a pretty simple, naive approach to accessing these CSV files and printing out the user data. So if all we ever needed to do was access, an address or a first name by student ID, then this scheme works out pretty well for us. But let's imagine that there are some different problems we have to solve, some different questions we need to be able to answer, such as, what if we need to find a student record by name instead of ID number? Or if we need to list all the students enrolled in a particular course. Or hardest of all, so to answer these kinds of questions, we would probably have to loop through all of our CSV files and open up each of them. And then, for like list of students in a particular course, look at every course that each student is taking just to find all of the students that are in a particular course. That's not very efficient. So we would ideally like to have a better way to interact with our data that lets us easily, efficiently answer these kinds of questions. So I'm hoping it's clear enough at this point that it would be hard to answer these kinds of questions with a CSV-based application. You'd end up writing a lot of code just for, querying your data, answering these kinds of questions about the data that you've got. So we're going to have to think about a different way of accessing our data, a different approach. This is commonly called a relational approach to databases. So some decades ago, this was 1970 by a guy named E.F. Codd, wrote a paper, Relational Model of Data for Large Shared Data Banks. This is not required reading, but if you're really curious, we do have a link to it here for you. I think it's interesting sometimes kind of reading these papers that are really foundational for the web, but since a lot of them are really old, it's going to be maybe hard to make a connection between what you're reading and what we actually do today. But there's one thing that I think is really interesting, a lot of good quotes in here, but really the first sentence I think is kind of interesting. Future users of large data banks must be protected from having to know how the data is organized in the machine, the internal representations. So this is fundamentally talking about abstraction, saying that the way data is stored in databases is a complex idea. And there's actually a lot of complex ideas that go into making that work. But you should be able to interact with the database without dealing with those complex ideas. But there should be some smaller set of simpler ideas that we need to think about in order to interact with our database. So the internal representation of our database is a lot of really complex data structures. I'm not an expert on them. Like I mentioned several weeks ago, that there's a sophisticated form of a binary search tree that's used in modern databases, but we don't have to know really the ins and outs of how that works. What we have to know is just the SQL language, SQL. So that's the abstraction we're going to work with in order to actually query our data. So this is part of the intention of SQL, is that the language itself is supposed to make it easy as possible to query your data, and you shouldn't have to know actually how the data is stored internally. So like in this example here, in order to query the data, we have to understand how it's stored internally, that we've got a dictionary with a nested dictionary, and then it's got a nested list. And so if we wanted to answer questions like list all the students enrolled in a particular course, we have to understand that there's a list inside of our dictionary, and then how to iterate through those kinds of data structures. In SQL, the intention is that you don't have to know how the data is actually stored. So the database is able to optimize your data storage and retrieval in ways that you don't understand. You just have to know the SQL language. Originally, this was intended so that actually non-programmers should be able to query SQL databases. SQL was supposed to look as much like English as possible so that you didn't have to be technical in order to query a SQL database. I don't think that promise has quite been delivered upon. You still do need to be a programmer to write SQL, in my opinion, and bad things happen when you let business people who are non-technical write SQL for your application. But that being said, it's still nice that, as a junior developer, you can get a practical mastery of SQL to build whatever you need to build without fully understanding all the internals of it. You don't have to be like a database administrator and understand all the data structures and B trees. So it is nice that the language SQL is much simpler than the actual internal data in these databases. So let's take another look at our school data here. Let's think about maybe a different way that we could organize our data instead of just putting it all in one big data structure. Because in a relational database, an important part of setting up our data is how it relates to each other. So we're gonna, instead of having all of our different types of data, all the different things that belong to one student in one data structure, we're gonna separate them into multiple tables. So every type of thing in a SQL database should get its own table. So we'd start out, let's say we're gonna have a students table. This might have properties for an ID, first name, last name, birth date, and an address ID. So the student has to have an ID so we know which student they are in the database. But then we're not going to actually put their address itself here. They get an ID for the address that's going to refer to something else. So then we would have a separate table for addresses. So this is going to have your address line 1, address line 2, city, state, zip code, and an ID. You'd have a table for classes, which again need to have their own ID, name, maybe number of credits for that class. And then we would need a separate table that connects the students with their classes, because this is going to be a little bit more complex than just students and addresses, because one student can have many classes. One class will have many students. We're going to talk in the coming days in this week about these types of relationships and how we model them specifically. But one way that we could model that, we might have a table called enrollments. Again, has an ID. And then it's going to have a student ID and a class ID. And so this is going to help us keep track of which student is in which class. Sometimes we might also put more information on a table like this to, further describe how a student is in a class or what it means for them to be in a class. So here, students for each class they're in have a grade. So we might add that as additional information. But the main point of this table is just to associate the students with their classes. So here we have a schema, a plan, let's say, for storing our data for our students. This stores the same data as what we have here in our JSON structure. But this is a more flexible way of storing our data. So we can query it in different ways and ask the questions that we want to ask without having to look at every single detail of every record, like we might have had to with our CSV files. So now I want to look back at these questions here that we're having trouble answering with CSV files. So I just want to show you real quick just how much easier it is now to answer these questions using SQL. So this is going to show you some syntax that we haven't taught you yet, but I just want to kind of illustrate the difference between writing several functions that loop through CSV files and just writing a single SQL statement. So for the example where you want to find a student by their name instead of their ID number, so that's a pretty basic SQL statement here. selecting all the information from the students table, but not for all students, only specifically students with the last name of Gardis. There might be multiple students, maybe you got some twins or something, or it's just a common name wherever the school is, I don't know. More interestingly, let's say we want to list all the students enrolled in a particular course. So we got a more complicated query that this involves two tables. So this was the relational aspect I was talking about before. We're defining how the enrollments table relates to the students table. Because the enrollments has the student ID, which should refer to the student's ID. And then for our last example here, something like that. We want to select people with the birth date in between a certain date range. This is an example statement, lets you do that. A couple of stylistic things that I want to point out here. A lot of these SQL keywords, you see me writing in all caps. That's not necessary. SQL itself doesn't care if this is like capital, lowercase, or like sarcasm, mixed case, or whatever. But it is very conventional that SQL keywords are written in all caps, and user-defined variables, like the names of your tables or the names of your columns, those are defined in lowercase letters. So this is just a convention to help you keep track, like visually, of what things are predefined in SQL and what things you've defined as a user. So this is the basics of what SQL lets us do. Lets us, query our data, know about the information we've stored. There are a few additional benefits that I just want to mention briefly. Other reasons why we use SQL databases. So first of all, databases are really good at scaling. So imagine right now we're reading CSV files on our local machine and it works fine because there's just one person trying to read it at a time. But imagine if you have 1,000 people connecting to your application and they're all trying to read the same CSV file. I don't know how well most file systems would deal with that if you've got a whole bunch of people trying to open the same file at the same time. So databases are designed specifically to allow multiple people to query data at the same time. They can accept dozens of simultaneous connections. But also, if that becomes an insufficient solution, that even accepting dozens of connections at a time, your database can't handle all of their traffic fast enough, you can combine multiple database servers together into a cluster that together will all handle the traffic from your users. So you may have heard this dichotomy before, but there are two types of scaling when we talk about scaling an application. Vertical scaling is where you replace a small server with a larger server, just one that's got more RAM, more hard drive, faster CPU. That's not particularly smart or cost effective, but it's generally simple to do. You just pay money and get a faster server. What I'm talking about here is horizontal scaling, where you don't use stronger machines, you just use a larger number of medium powered machines or low powered machines, but get them to coordinate with each other and share the load in an intelligent way so that it can, handle much larger volumes of traffic than a single server would be, or even a single larger server. So databases also provide you data validation. We can set rules on our tables and say, like, we should not be able to store a user without their birth date. It's just not valid in our application. We can't use that data. We can't run the app if a user doesn't have a birth date. So we would like our database to just throw an error if we try to save data that is incomplete or incorrect. So you can make sure that required data is present. Maybe another example of a data validation would be making sure that your account balance is always positive. If you're building an application that does financial transactions, maybe you don't want to allow people to spend money they don't have. So you can declare that their account balance needs to be a positive integer. And if it ever goes below 0, it's going to throw an error and then cancel all of the other transactions that led up to that deposit going negative, or to that withdrawal going negative. And so in that way, you can prevent users from spending money they don't have. Similarly, is data integrity. So this is more about how multiple people trying to access the same record at the same time don't leave it in an inconsistent state afterwards. So one way this is accomplished is just by locking, where if one user has a connection to the database where they're writing a record, they might lock it, and then no one else can access that record until the lock is released. Or also very important is databases support this concept of transactions, which means that you can group multiple queries together and say that if any of them fails, all of them should be reversed. So the classic example of when you should use a transaction is for transferring money. So let's say I'm trying to, give Ankur $10, transfer it from my bank account to his bank account. So you could do that with 2 SQL statements. You would decrement $10 from my account balance, and then you would increment $10 on Ankur's account balance. But if we imagine that like the application throws an error at some point while it's doing this logic, like maybe it throws an error while trying to increment Anker's account balance, then the first SQL statement ran, I lost $10, but the second SQL statement didn't finish. And so Anker never got that $10. So we didn't actually transfer money, it just disappeared. So if you're building a financial application, that's unacceptable. You need to use transactions. Honestly, if you're building any kind of application, you need to use transactions, but it's most obvious why you need them for financial applications. So we would use a transaction to say that first, we're going to decrement $10 from my account, and we're going to try to increment $10 into Anker's account. But if that fails, we're going to undo decrementing $10 from my account so that if anything doesn't work as planned, we just revert back to the situation we were in before we started. And lastly, SQL is very helpful with filtering and searching. Excuse me. Now, we might take this for granted a little bit because we've been doing a lot of filtering and searching already. Just using Python or JavaScript. But now, as I'm sure you've noticed, Python compared to JavaScript has much nicer tools built in for searching and filtering your data. It just does a little bit more for you automatically. It's slightly higher level. So SQL is kind of like that to Python. In SQL, we're going to have even more advanced filtering and searching tools and sorting tools that will allow you to apply advanced functionality without actually coding yourself. You just have to understand what you're asking of the database and how to phrase it, and the database does all the complex logic for you. So something I've heard people say a lot in the past is that you should let the database do what the database is good at. One of the things that your database is good at is filtering, searching, and sorting. Your database is going to be able to do this much faster than you would be able to do it in Python or JavaScript. So like I was saying before, oftentimes there's work to be done in code, and it's unclear if you should do that on the back end or the front end. So here you could filter your data in SQL and then send to the client just what the client needs, or you could send to the client all the data in the database or all the data in a table, for example, and then have the client filter it down to just what they need. But generally, that's going to be pretty slow if you try to do a lot of filtering like that in JavaScript or even just in Python, whereas the database can do it really fast. So if you're trying to do something that the database is capable of doing, try to leverage the database's capabilities as much as possible. All right, so that is some kind of basic background of what SQL is and what problem it solves, why we use it. Next, I want to go over just some basic syntax, just so you're kind of comfortable reading SQL before we actually get started writing some. Does anybody have any questions, though, about any of this background information before we take a break and then go to the next section? Andrew?
I actually have a question. So we talked a lot about like the benefits, but about the negatives. So I'm guessing off the top of my head, the hard part about databases is like a lot more effort has to be put into like the design of it in the first place. And for a simple project, maybe just like something simple like a CSV file would be easier.
I think it is true that you have to be careful about the upfront design of a SQL database, but I think that would also be true using CSV files. Just because CSV files are so much more limited than a SQL database, you would have to be much, much more careful about how you designed your application, and it would still probably be clumsy to work with. as much as like important database design upfront is important, SQL is also fairly flexible. So like if you're smart, there are kind of agnostic ways you can design your application so that you can still change it in multiple directions later down the road and still not have to do too much changes to your SQL. So yeah, I would not recommend ever building a serious application that uses CSVs as their database, no matter how simple it is. Even if I was gonna like build a 2-hour project, if it needs to have persistent data, I would put in Postgres or maybe SQLite as a database. Yeah, databases are really doing a lot of work for you, solving a lot of problems. I don't think there's any project small enough that I would use something else really, unless you just don't need data. Does that make sense?
Yep, thank you.
Any other questions? Questions going once, going twice. Okay, let's take a break now. It's 10:07. Come back at 10:20, and I'm going to show you some basics of SQL syntax. Hello, folks. Welcome back. Hope you all enjoyed your break. Right now, if we don't have any other questions right now before we get started, I'm just going to chat a little bit about the actual syntax of SQL, what this looks like. Then we're going to maybe start writing a few commands later on. So for a little background on just types of databases, we're focused on this class mostly on relational databases, SQL-based databases. So this little diagram on the left here should show you what I was talking about. We've got the multiple tables that each have just one type of thing in them. And then we also define relations between those tables. So, the customer relates to order because the order has a customer ID on it. Order relates to order status by the order status ID, whatever. Everything has IDs on it that relate them to other tables. So an alternative to that, there are non-relational databases. This is often called NoSQL, which is an acronym for not only SQL. So it's basically any database that is not a SQL database can be considered a NoSQL database. One example of those that you might have heard of is MongoDB. There are a bunch of others though. Commonly, they'll store your data in more of like a JSON-like format, or you have dictionaries and lists. So that's kind of what you can see on the right here, where you've got one big top-level object, and it has lists inside of it with dictionaries. As we're learning about practically how to interact with our SQL database, there are two main halves of this, two main components. We're going to talk about how we're storing the data. So with our tables and columns and rows. And we're also going to talk about how we query the data using the actual SQL language. These are going to be kind of the two main components of what we're learning. So like I was saying before, the main feature of a SQL database is the table. This is going to be like your main unit of organization, I guess, for your data. Excuse me. So this is a basic example of a student's table. Remember, every table needs to have an ID. It does not have to be an integer, but very commonly IDs are just going to be integers starting at 1, counting up. It's probably the simplest way that you can have a unique ID for everything in your table. And then whatever other data you need to keep track of. So yeah, important terminology here. The whole thing is a table. We have multiple columns. The columns are basically the fields or the attributes of your data. And then the row is one individual piece of data, like one individual student would be a row. Sometimes a row is called a record when we're dealing with SQL databases. So those are kind of synonymous terms. that I might use. Now, another important term when we're talking about databases is a schema. So a schema is kind of like the plan for your data, just the specific tables you're going to use, the specific columns that your tables are going to have, and the types of those columns. And then there are other aspects to building a schema. So there are like constraints is another thing that we'll learn about later, like null versus not null, and indexes and things. But this is kind of the core of your schema. What are my tables? What columns do I have in those tables? What types of data can I put in those columns? So probably the first command that we're going to use in SQL is create table. It just creates it. Well, first we're going to create database. Then after we create a database, we will create a table. And then after that, we can actually start inserting data. So you can use just about any name that you want. Although if you choose a very poor name, it can be kind of hard to read your SQL code and just hard to compare your table names to other pieces of data, other things you have in your application. So these naming conventions are, I think, pretty important to make it easy to read. So commonly, you're going to use lowercase letters for your entire table name, and you're going to use a plural noun. So this is different from how we named our classes in object-oriented programming. And this is honestly a minor point of conflict that I've had to struggle with throughout my career. If you have like an object-oriented class, you know, like for students, you probably use a singular name, student, but a table for students would be lowercase s, plural students. So you're using slightly different naming conventions, whether it's an object-oriented class or a SQL table, even though conceptually these are kind of the same things. It's a group of students. So just be careful of these naming conventions. The way that things are named can help give you clues as to what it is that is being named. And like I said before, very common practice to have a unique integer as the ID. So every table needs to have an ID, and integers are a pretty common way to do that. So this is just kind of an example of how you might convert, or how you might name a table based on what that table stores. Just giving an example, you know, lowercase letters, no spaces, prefer underscores over dashes. I'm not sure why. I don't think I've ever seen dashes, or no, I definitely have seen dashes in a SQL table name, but it always looks really out of place. It's very conventional to use underscores for a SQL table name. And definitely feel free to, you know, interrupt at any point, ask questions about any of these slides. I know this is probably the first time that a lot of you are seeing this and might have some like simple basic questions or whatever. All right, so for the columns, that's each field in our table, we're going to use similar naming conventions. Just use lowercase letters, underscores, connect words. And then typically you're going to use a singular noun or adjectives. So, you know, first name, last name, I think that's pretty obvious. We just use a noun for those things. For Boolean variables, you usually want some kind of adjective like is active or on probation, something that sounds like it could be a yes or no question, true or false. So beyond choosing a good name, you also have to declare the types for each column. So this is part of our data validation. Our database is going to make sure that, you know, if the first name is supposed to be a string, we can't just put a number in there. That doesn't make any sense. On probation has to be a Boolean. You can't say that on probation is 6. That doesn't really mean anything. They either are or are not on probation. So we get to define the types of our data just so that our database can validate it and help us prevent bad data from getting in. So I think most of these are going to be kind of familiar to you, except for varchar is probably not a term you've heard before. This essentially means string, just a varying number of characters, up to 255 of them. So depending on how long the field is supposed to be, you might use a smaller varchar field. So for social security number, for example, there's no reason why anyone's social security number should be longer than, what is it, like 10 or 15 digits, depending on whether you put the dashes in or not. Yeah. So a relatively small field is sufficient for a social security number. Whereas for names, like maybe someone has a very long name that's like, you know, mother of so-and-so, son of so-and-so, son of so-and-so, descended from the town of wherever in the state of such and such, from the great nation of wherever. You know, some people have really long names that translate like that. So maybe for last name, I don't want to actually limit that to being like 30 characters. I'll be open-minded, make it much longer, 255. But for some things, you know that it's supposed to be a short string. And so you can help the database store that data more efficiently by telling it this is never going to be longer than, you know, however many characters. So these are some pretty common types that your database might support. So different databases will support different types, just heads up. You know, between Postgres, MySQL, Microsoft SQL, Oracle SQL, they will support slightly different types. Like for example, in Postgres, I know one of the kind of newer features of Postgres that I think is pretty cool is that there is a JSON type. So Postgres actually has specific functionality for storing JSON data and querying it, which is really weird because that's kind of the opposite of what you expect from a SQL database. You expect to like not be working with JSON data. That's what you would do in a NoSQL database. But apparently, if you want to really get some kind of hybrid SQL, NoSQL solution going, Postgres does have that data type. But that's not a common thing in SQL databases. That's not like conventionally how you would design a SQL database. And so it's not in our table of common data types here. More commonly, what you're going to deal with in any SQL database, you've got integers, you've got decimals. So if you actually need to do financial math, the decimal type in your SQL database is probably going to be a lot more precise than using floats in Python or JavaScript. I think a lot of us might have observed like dropping pennies for the change-making exercise. In theory, that should not happen quite so easily when you're doing math with SQL. We have text, which is basically the same as varchar, except instead of, you know, being some small number of characters, you know, hundreds or tens of characters, it's much larger, maybe like thousands of characters. So like if you were going to store a blog post in the database, you would probably use a text type field because that's going to be like pages and pages of text. So the downside is that text fields, I think you can't search them as easily as you would a varchar field because they're so much bigger. But sometimes you need to have bigger chunks of text that you store, and so this is the way you do it. Another important thing that your database is going to store is going to be dates. Unfortunately, there's a lot of complexity in working with dates. This is probably going to be one of the most complex things you're going to have to store in the database. And I'm going to tell you from my experience, most of the bugs that I've struggled with dealing with databases in like live production environments came from somebody not understanding how dates work. Either some engineer who designed the system or like some user who's trying to type in dates and they were just like typing in weird things that are not actual dates and we didn't validate it well enough. So I guess that's still an engineer's fault. But definitely dates are not as intuitive to work with as you might think. So just spend some time, make sure you understand them. And it's a little bit different in different programming languages as well. JavaScript handles dates a little bit differently than Python will. But you just have to know if the date has time or not, if it has the time zone included. Handling time zones is tricky often. Ivan, do you have a question?
I just had a question. I remember reading something that it was the column type was real and not decimal. I don't know if that's they're looking at a different column type.
I think Postgres might support both of those as types, actually.
Okay.
I could be mistaken though.
Okay, so we can use real or decimal for the fractional number.
Yeah, I think one is more like real is more for like fluid quantities where like you don't know how many decimal points you might need. Where decimal is more for like doing financial math where you know you need exactly 2 decimal points. So like both of them deal with non-integer numbers, but the use case is slightly different, I think.
Okay, thank you.
Yep. There were 2 other hands. I didn't see the names.
Can you hear me?
Yep.
Oh, good. Under column type for varchar, I was wondering if those brackets are set like that on purpose or if that's a typo.
That's a typo. Thank you for
Okay.
pointing that out. Let's see, actually, why don't I just do this real quick here.
I'm glad that's a typo. That scared me a little.
Yeah, you should be terrified if you ever see mismatched brackets like that and someone tells you it's correct. So yeah, the actual SQL syntax here is the parentheses. You would type varchar parentheses and then some number. The brackets here is just kind of like for documentation. Sometimes people write brackets in documentation just to indicate like options, essentially. So this is saying that I can call varchar with parentheses and then pass in some number between 1 to 255 to specify how many characters I'm allowing in this particular field. Thanks for catching that. There was one other question, I think. I know I saw 3 hands, but maybe you forgot what was on your mind. So an important topic that I want to talk about for a little bit here is schema modifications. So of course, you know, the first draft that you make of anything is not going to be the last draft, possibly that you didn't build it right to begin with. But more likely is that even if you did build it correctly or good enough to begin with, your boss is going to come in someday and say, you know, requirements have changed, we need to pivot, we're doing this other thing now, or we just acquired this one really expensive client, really valuable client, they're going to pay us a boatload of money to add this specific feature, and we need to update the database to support that. So even in the best of cases, you will need to update the database over the lifetime of an application. This is commonly called a migration, a schema migration, or you're migrating the database. I think that's kind of a strange term because it doesn't necessarily mean you're moving it to somewhere else. Like the database might still be deployed in the same location. It's not like moving from like California to New York or whatever. But the migration means that you are changing the structure of the data. So maybe you're adding new columns, you're adding new tables, or maybe you're changing the type of an existing column. Those would all be considered migrations. But this is a fairly expensive process. Like it's easy to mess up, I'll say. You want to be careful that you don't like do anything terrible to your database. So like you have to take your time when designing schema, take time when designing your migrations to make sure you're doing the right thing, because this is code that you're going to apply to a live database. So what makes changing your data schema so much harder than changing the code is if you decide that like one of your algorithms in the application isn't good, it's inefficient, you want to replace it with a more efficient algorithm, you can just like take down the server at midnight for maintenance and then put up the new version the next day. And it'll have the new and improved algorithm and everything will run faster and there won't be any problems. But if you decide that your database schema needs to change, you've got big issues because you already have existing customers using the old database schema. You can't just like take down all the data and then start with the new fresh database with the new schema, because then you just lost all your customers' data and you're probably going to go out of business if like you just lost all of your customers' data at the same time. So the way that we do this is by writing migrations. These are SQL scripts that developers write, basically saying that, given the current state of the database, what do I need to change in order to get it to the next version of our database to migrate it there? And then ideally, you also write a script that goes in reverse. So you write a specific SQL script that will reverse the changes in that migration in case you need to undo what you did. You changed the schema to a new version, you determined that that was actually a bad idea, you need to go back to how things used to work. So you use your undo SQL script that undoes that migration. Ideally, then you also name all these migration files based on the date that they're created. So that way, if you have a new deployment of your application and you want to get the database up to speed with the current way that the database is supposed to look, you can just run all the migration scripts in order. And then that should apply, all the changes that you've made to the database in the order that they were made, so that then this newly deployed database should have the correct up-to-date schema. So then those files would be committed in Git so that other collaborators of yours, when they pull down the project, they're able to run the migrations themselves and get their local database up to speed. So I want to reiterate that writing and running migrations is an important part of managing a database. This is something that you should be familiar with, this problem and why you have to do it, why this is precarious. But we're not actually going to do that in this course because Django does it for you. In my opinion, this is one of the nicest features that Django has. We're going to be learning about the Django ORM later this week. And as you're going to see, Django will automatically manage your migrations for you. This is, in my opinion, just an enormous time saver. And it also just prevents you from making lots of bugs, lots of mistakes. You're going to tell Django what you want your data to look like in Python, and Django is going to automatically create these migration files for you. You don't even have to look at them. You just have to tell Django to make them for you and then tell Django to run them. But a lot of these steps in updating your database are managed for you automatically. So I just want you to appreciate that there's a lot of work being done here for you automatically, that if you go to any other server framework, you're probably going to have to do it more manually, or at least look at it a little bit closer and understand how it works. So I just want to take a few minutes here to talk about it, because I don't think we're going to cover that formally at any point, given that Django does it for you. And also, just as a general statement, like even aside from writing migrations, it's a good idea to spend extra time planning your schema and make sure that it makes sense for your application. Try to predict the ways that your application might grow in the future, and make sense that your schema isn't going to cause problems in the future if your application grows. Like, can you handle a few ways that your application might potentially change without actually doing a huge migration? Now, that doesn't mean that you should like write your schema to fit an application that doesn't exist yet and might never exist. Like, to some extent, you want to write your schema to serve the current application as it exists today. But there's also a balance about future-proofing it, so you don't have to do a lot of dangerous work if you're asked to do a migration, which you could reasonably expect. So you're going to need to keep the single responsibility principle in mind when you're building your SQL databases. So this is just kind of another way you can think about how to build your tables, just that each table should do one thing. It should only keep track of one type of data. If you find yourself storing multiple types of data in the same table, then that's very likely to cause you problems going forward. So let's just look at an example of that real quick, just to see the kinds of problems that we might have storing multiple types of data in one table. So this is a problematic table here. We've got the user's information and their address kind of all stored on one line. And in theory, this kind of makes sense that, you know, a user has an address that belongs to them, but other people live at that address too. And also it's possible that the user might have had other addresses in the past. So this is not a very flexible data structure, not a very flexible way that we can store all the information about our users. Because again, this is really two different types of things, our student and their addresses. And remember, one of our goals also is to avoid duplicating ourselves, avoid repeating ourselves. There are ways that we could split this up into multiple tables that involves repeating our data, but that's even worse than just having it in one big table. So here's kind of an example of that. We've got our students table, their first name, last name on probation, and the addresses table to keep track of all the student addresses also has the student's first name and last name of whoever lives at that address. So this is a problem because this is creating duplicate data. Now, if we want to change a user's first name, we would have to do that in two different tables. We'd have to go to the students table, change their first name here. And then we'd also have to remember that that data exists in the addresses table and update it here as well. So that's just extra burden on the developers. Every time you change any of the data anywhere, you have to make sure you change it everywhere. You have to make sure you did it consistently. You have to make sure if there was an error, you know, you didn't change it in one place and not others. You can definitely get into problems where you have duplicate data, but it doesn't get updated consistently. So you might have, you know, first name here says Tiana, and then first name over here says Tammy, and you're not really sure which is correct. So it's really important that you have canonical data, that there's only one official version of each piece of data in your database. So yeah, this is just kind of posing the question that I just asked. If a student changes their name, we're gonna have some big problems. So let's think about an alternative schema that we can use to eliminate this duplication. So this is illustrating that relational aspect that we were talking about before. On our students, now instead of giving them the address itself, they just have an address ID. So this is just kind of a connection, a reference to a record in another table that has the rest of their data. So students with the ID of 1, Tiana Lowe, their address ID is 4. So to know what that means, we have to look at the addresses table. And the record with ID 4 is this address. So that's how we relate those two tables together, figure out the student's address without storing redundant data. Andrew?
So different tables with the ID numbers, would you want to restart over again at like ID 1 or 2? Because in the last example, like it went from 1 to 2 to 4 to 5. But can't you just have a bunch of different tables where it all starts from 1 to 10? Or is that like a design decision or choice?
So in this particular case, yeah, they could all start at 1. There's no particular reason why the ID starts at 4 here. Let me think here. So when you start your table, if you just use the simple IDs, like Postgres has an automatic feature that can set the IDs for you. And if you use that, it'll just start at 1 and count up. So if you just do it the simplest way possible, all of your tables will start with ID of 1 and then just count up from there. Although it's possible that if like as you're debugging and developing, you might delete some records and then create some more, but it's not going to reuse those numbers. So maybe if you created 10 students and then deleted them and then created 10 more, you would have students 11 through 20. So it's possible that if you look at your data, it's not going to always start at 1, but I wouldn't say it's a design decision to make it start at any other specific number. Sound good?
Yeah, that sounds good.
Cool. Jesse?
Yeah, how is the address ID being tied to the addresses ID table on the students piece? I mean, like, how does it?
Like, what is this line that we're drawing here?
Well, more so, how are they being connected code-wise?
So let me just take you back real quick to some of those SQL statements I showed you in my editor. So this middle one here is going to give you an example of that. It's the join statement that lets us relate two tables together. And then this logical statement here is saying what the relation between those two tables is. So it's saying, hey, from the students table, they're going to have an ID. And then in the enrollments table, there's going to be a field called student ID. If you find any records from both those tables where that's the same number, then that means that those are matching records and they should be merged together in the output. So again, we're going to learn, I think this is going to be tomorrow more. You're going to learn more in depth how to use the join keyword in SQL. But the simple answer to your question is join is how we relate those two tables together in code.
Awesome, thank you.
Yep. Brian?
So is it safe to say that are we always looking at the primary keys when we're doing our joining from table to table? Is that how we're making that link normally, or are we linking outside of the primary keys when we're going table to table and putting info together?
I'd say 99% of the time, if you're lucky, you're just relating a primary key in one table to a foreign key in another. So, you know, this ID, this is the primary key for addresses because it identifies the address itself. These 4 and 5 in the address ID, this is the foreign key for students because it identifies a record in another table, a foreign table that relates to this one. So ideally, all of your joins are just foreign key to a primary key. That's probably the simplest and most straightforward way to join tables. And in a well-designed database, that's probably the only type of join you'll need. I've been in some kind of interesting situations where I've had to get a little bit more creative with my SQL queries and had to join other things together that were not keys. So like in this example here, this logical statement of how to join the tables, we're only looking at 2 keys. You know, if this primary key on the students table is equal to this foreign key on the enrollments table. But this logical statement could be comparing anything, any fields in these 2 tables. So like the example, the craziest SQL query that I can remember having to write was for like a food service app. It was letting users query for different recipes and then query for like different ingredients in those recipes. But one of the things that made this application tricky was that some of the recipes could themselves be components of other recipes. So like, you know, one recipe might be a burger, which has ingredients of like bun, patty, lettuce, tomato, whatever. And then another recipe might be burger and fries, which has as its components burger and then also fries as an ingredient. So I had to be able to join a table onto itself, which is not something you do very commonly in SQL, but it was the right solution to this problem. So long story short, you can join anything on anything, but I'm hoping that you don't have to get too creative in your career and you just do simple things like this.
Thank
I hope
you.
that- You're welcome. So we were talking before about data integrity and just making sure all the data in your application makes sense. So this is a pretty common example of just preventing duplicate signups. So maybe you've had the issue happen in the past where you're trying to log into a website and you've forgotten your password or it doesn't let you log in. You think maybe I just don't even have an account. So you try registering and it tells you that you can't sign up because that email already exists in our database. So this is one way that you can implement that is by using constraints in your database. You can enforce uniqueness on a certain column. So very commonly, on the email column for your users table, you would set the email to be unique. There's no reason why you should let multiple accounts have the same email. Because then also when someone logs in, you don't know which password is valid. You don't want someone to have multiple valid passwords. That doesn't seem right. You're not supposed to share accounts on this hypothetical web application. So yeah, this situation here, got two users with the same email. Ideally, we should prevent this automatically with our database. All right, so pretty soon we're going to be writing some queries. Pretty much any command you give to SQL is a query. Even when you're creating data and you're not like trying to read data, you still call that a query. That's a little bit unintuitive, you know, based on how English works, what the word query means, but this is how SQL works. There's a whole bunch of commands in SQL. By far though, these are the four that I use most commonly. Like 90% of your queries are going to be selects, handful of insert and update, and then every now and again you delete things. Honestly, most web applications don't really delete data like ever. So that's probably the least common operation here. So starting simple, the most basic SQL query you can write, selecting all data from all records, would just be select star from students. So we're only selecting from the students table, but star means that we're selecting every column. You know, we could choose more specifically if we want ID, first name or last name or some combination of those columns. But in a lot of cases, especially just as we're getting started learning, you might just want to get all the data. So select star is how you do that. And this is what the output would be like at your command line. It's going to give you this nice pretty little table and then show you all of the records that matched your query. So like I was saying before, you can specify the rows that you want or specify the columns that you want returned. So here we don't care about the last name. We're just going to get ID in the first name. So if we had like a really, really enormous table, this might help us to get less data instead of wastefully transferring more data around that we don't need. So typically it's not useful to get our entire table. We want to get only specific records from our table that match certain criteria. The way we filter our results is with the where clause. So just at the end of your query, you say where, and then any logical condition. Excuse me. So here ID is referring to the ID from the table. So whichever student has ID of 2 is the only one that gets returned in this query, which is Elda. Tiana has ID 1, so she doesn't show up. Now, if you want to control what data matches your filter. There are a lot of different operators you can use. These are pretty similar to the operators that we use in Python or JavaScript, but there are some differences. Like for some reason, SQL has this double caret sign thing as the not equal to operator, which I think is kind of weird looking. I guess it's supposed to be like less than and greater than simultaneously, which means not equal to. I don't know. I prefer using bang equals because they do the same thing and it's more familiar looking to me. It has a lot of other familiar operators. And you can look these up to see what other ones it has that might be useful. Actually, I'm just going to do a quick Google, see what we can see. Looking for comparison operators. Oh, so this is that same table that we just showed you. Oh, wow, this is not super detailed. Okay, here's a lot more operators. So there's like, which helps you get like fuzzy matches, not exact matches. You can use regex matching. You know, you guys all like regular expressions. Got modulo. So yeah, a lot of operators. It's probably more flexible than JavaScript or Python or whatever programming language you're using. So if you need to compare things in tricky ways, definitely check out what other operators Postgres supports. Porphy?
You're muted.
Yeah, you're muted. Forfeit, you're muted.
Oh, thank you, thank you. Sorry. So I just wanted to make sure you can do your select for any titles, and they don't have to necessarily be also one of the things that you put for your where. Like I could just look for select, let's say, first name, and then just from students where ID is 2, and it'll just give me the name, right? I don't have to also have the ID for it to work.
Correct. Yeah. I mean, yeah, so you might think it's obvious that the ID is 2 because you asked for the person with ID of 2. So in that case, you might say like, I don't need to get it in the output. Me personally, I kind of like seeing it here. IDs make me feel comfortable. But yeah, if you just thought you didn't care about it, you could just say select first name from students where ID equals 2.
Cool.
SQL knows that ID is a column on the students table.
Awesome.
Yep.
And then a second thing, we can't modify data directly through SQL, right? We have to feed it back into SQL after we've already modified it.
Oh, you can totally modify your data in SQL. Select will not modify your data, but insert, update, delete, those are very destructive. You got to be careful running these commands, especially on a live production database. You know, if you accidentally run a delete command without a where clause on the production database, you're going to delete everyone's data and probably lose your job.
Gotcha. Make a note of that.
Got some hands up?
Yeah, I have a question. So will SQL throw out errors if you're trying to do like one of those, if you're selecting something greater than, but what you actually have in your field is like a string, will it throw out errors or will it just like go past the thing and do nothing?
So in that case specifically, I think SQL can actually make sense of that because the greater than less than operators will alphabetically sort strings.
Mm-hmm.
But there are some cases where you could give an operator for some operand that just doesn't make sense.
Mm-hmm.
Can't think of a great example at the moment, but SQL will definitely throw errors if you ask it to do something that just does not make sense.
I'm guessing it has to be more part of like your original design because you can limit your entries to like be of a certain type, right?
Yeah.
Yeah. So you just have to be smarter when you design it instead of asking weird things to SQL.
it is generally good to be smart when you're designing your database. These things are easier to get right up front and kind of painful to change later. Rob?
So going off what you said about the mistake you can make with like delete or just modifying data, is it more common to work in like almost like a virtual environment for a database before changes are made, or is there some sort of like safety net involved with modifying data on a database?
I mean, it's common that developers won't have actual access to the live production data, and they're going to be working with kind of like fake or dummy data on their local machine. And then if you're reasonably confident that it works on their local machine, then they push it up, gets code reviewed, gets merged into the develop branch or the master branch, and then you deploy it to a staging server, which is supposed to be a real live deployed public server that just doesn't have millions of customers hitting it. So it's supposed to look as real as possible and behave as much as possible like the real application. Just it's not actually publicly viewable. So if it fails, then nobody's going to yell at you about it. But there you can actually test if your schema is working the way you think it should be. And then if it actually works there, then you can deploy it to the actual real production application. So it's a series of tests that get progressively more and more realistic. It's definitely, I would say, hard to verify that your schema is perfect if you're just testing it on your local machine. I've run into lots of bugs as a professional. Certainly the very worst bugs I've had to deal with as a professional have had to deal with the differences between how the database runs on your local machine and how it runs on the server. So I try to run my database in as server-like of a way as possible and get comfortable with testing my applications on live servers just to make sure the database works how I think it should. Were there other hands up? No? Okay. Oh, so this last example here is pretty nifty. This is showing a like query. So this isn't looking for classes where the name is art. This is looking for classes where the name is like art. More specifically, starts with the letters ART and then ends with anything. So in SQL, the %sign is a wildcard, means just any number of any letters. So like I was saying before, we can insert data using SQL. This is definitely destructive. We can create and modify data as well as just querying it. The insert statement is how you do that. Say insert into, and then the name of the table you're inserting data into. Then in parentheses, you say the columns that you want to insert data into, the word values, and then in parentheses again, the actual values you're inserting into those columns. Now it's really important that these things match. There's 3 items in this set of parentheses, and there's 3 items in this set of parentheses. The order matters here. So we're saying here, first name is going to be Michelle, last name is going to be DuPont, birthday is going to be 1982-02-11. So this is kind of like defining a function that uses ordered parameters and not keyword arguments. So when you're inserting data, it's important that you put everything in the right order. Sean?
Yeah, so you're saying it has to be positional. Like, is there a way to make it like keyword arguments or no?
Yes. So that I don't think that's actually like a natural feature of SQL itself to have keyword arguments, but like in your application, you're not going to be writing raw SQL that you send directly to the database. You're going to be using some program that sits on top of SQL that helps you interact with it, some SQL client. And that client is going to have some functionality that lets you write a SQL statement, not with the actual values, but with placeholders. And then you can also pass in an array of all the placeholder values. So practically speaking, a lot of the ways that you would actually write SQL using like actual practical professional tools, they will let you use named parameters or keyword arguments. But it's not exactly like a native SQL concept, if that makes sense.
Yeah, thank you.
It's definitely an important thing to think about because that's like a really big security vulnerability in SQL is the fact that the data and the queries are all mixed together in this one statement. There are a lot of opportunities for, clever hackers to make our server run code that we didn't expect it to. And one of the ways that we get around that is by these parameterized queries, what I was just talking about, how we have these tools that separate the query from the actual values. Did I see another hand up?
Yeah, I had a question, Raphael, about sort of like insertion and like kind of like the bigger theory thing. So kind of like how you said like SQL is kind of like for programmers in a way. Like if we did something like a school system, couldn't we make it so that everyone, like people that don't know how to program, just input information into Excel and we write the migration to do it for ours into SQL, and so that they never touch SQL in the first place?
Potentially you could do that. You might be surprised that it's difficult to get non-technical people to understand join tables, and just that like they shouldn't have duplicate information in multiple places. Like the student's name shouldn't be in the address table, it should just be addresses with a link to a student ID. If you can get people to understand that, then you might have good success just having people fill in an Excel spreadsheet and getting that to sync to a SQL database. But that can be just kind of precarious just with how much control you're giving non-technical people directly over the database. Like I don't know, what if Excel automatically formats your values when you paste them in? It replaces the straight quotation marks with the bendy quotation marks, or like Excel automatically formats dates in really aggressive and kind of awkward ways sometimes. Or somebody might just like accidentally misclick and like just accidentally delete a column because they got fat fingers or whatever. So you could potentially do that. I could see that working, but there are a few reasons why that makes me nervous. In general, though, I would say Excel is a really good tool for technical and non-technical people to interact with each other. But that's largely because Excel can export CSVs, which we can import. Any other questions here?
I have a quick one, and I might be just getting ahead of us, but when later on when we're using SQL databases within our programs and we need to like iterate through some data that's in SQL, do we have to pull all the data from SQL, like say like select star from students, and will that give us a dictionary that we iterate through, or is there like a better way that we're going to learn how to do that?
So many ORMs that you might use, or like many clients for querying your SQL database, would work in that way. You would like write a SQL statement and it would give you back a list probably to show all the records that match your query. But in Django, we're going to be interacting with our database on kind of a higher level. So you're only going to really be writing raw SQL just at first as you're learning about how SQL works, and if you're like debugging it, because if your app isn't working the way you think it should and you have to open up the hood and see what's actually going on, you're going to be writing and reading SQL statements at the console to figure out why it's broken. But practically speaking, if everything is going according to plan, you're going to be using Django to interact with your database. And the way that's going to work is you're going to write object-oriented classes in Django that are going to map onto your SQL tables. So instead, you're going to be calling object-oriented methods on like a student class or a person class. And then Django is going to be automatically translating that into SQL statements that operate on your tables. So in theory, it's supposed to prevent you from having to think about SQL code constantly. It's supposed to save you from bouncing back and forth between SQL and Python constantly. You should be able to just work in just Python for hours at a time unless, occasionally there's a problem in the database and you got to drop down a level and start looking at SQL. But for the most part, you should be able to work in just Python when you're working with your database. That's the intention. Does that help? Does that answer your question?
Yeah, when you say that we're going to be working essentially instead of SQL, we're going to be working with classes, you mean so like it'll be like how we had the init and we had like a bunch of things defined within each class already. Those would be our tables and our columns.
You're going to define data in your class for the columns, for like the fields, like first name, last name. Those are going to be the attributes you define in your class. You can also define methods in your class for like ways you can validate the data. But that's probably not the first thing you're going to do when you start defining these classes for your ORM. But most importantly is these classes that you define are going to inherit from a class that Django defines for you. So through inheritance, you're going to get access to a lot of automatic functionality, just, the insert and select methods. Like you don't have to define how to search your collections for specific records. Django is going to define that for us. We just have to define the bits that are unique to our application.
Okay, thank you.
Yep. So yeah, here we can insert. Here is update. This is where things are getting a little bit more dangerous now. So this is how we change data. Excuse me. So for example, if we want to change the addresses table, we have to choose which variables, which columns we want to change. So we're going to change address line 1. We're going to change their zip code. So we use the set keyword and just say key equals new value, key equals new value. And then very importantly, a where clause saying which records we want to apply this to. So let's do a little thought experiment real quick. What if I was typing out this query and I just forgot this last line and then I hit enter without thinking and I just ran the query? What happens if I forget this last line? What do we think?
Would
All
it
of-
change?
All of them will change.
Yeah, it's going to update every address in the database to set this, because we didn't specify which addresses we're updating, just does all of them then by default. So for this reason, like personally, when I write update or delete statements, I will write the where clause first, just to guarantee that there's no way I'm going to execute this statement without writing a where clause. It's like a little bit weird to write it that way, and like grammatically it doesn't flow, because grammatically that flows nicely if you read it from top to bottom. But I just want to be darn sure I don't accidentally run this command without the where clause. So I write it last. Then delete is the same issue. Don't write a delete statement without a where clause or you're going to drop the entire table. Kat, question?
Yeah, is there any type of like undo for tables or no for
Nah.
SQL?
Nah, just be careful. Ideally, you should be taking backups of the databases. So in a well-functioning organization, you automatically take backups at specific intervals, depending on how important your data is and how often it changes and how expensive it is to lose your data and how likely that is to happen. You might have different backup strategies. Maybe you back it up every hour, maybe you back it up every month, depends on the application. But in general, you should hope that if you accidentally run one of these queries that just like loses a whole bunch of data, at the very least, you lose the last hour of data or the last day of data, but not like literally everything all of your users have stored. So yeah, database backups, because there's no command Z for these commands we're doing. Sound good? I guess so. All right, so here, this slide is basically just cautioning you against what I was just telling you about. If you do not have a where condition with your update or delete, bad things will happen. You're going to have a much broader impact than you intended. It's going to end poorly. So just make sure you don't do that. All right. And that is all I have to say about the basic syntax of SQL. I think it's time for a break. And then when we come back, I'm going to show you a little bit about installing and managing, maintaining Postgres on your system. And then we might actually create a database, create a table, some fun stuff like that. Jesse, do you have a question?
Yeah, just a quick one. Can you add a new column or something if you needed to do that as well with insert?
Not with insert. Things like that where you change the table structure, that's done using a command called alter. So it's a good one. This is okay. Normally I try to avoid W3 schools as a source of documentation, but this is good enough for now. So there are a lot of different ways that you can change the schema that will all use the alter command. So you can alter table to add a column. I think that's what you were just talking about. Drop columns. Or you can just modify them to change their type to something else. There are other uses for the alter command. Hang on a second. Microsoft Docs. Like you can alter tables. I think you can use it to alter the database itself. They're just like a lot of things that you can change that aren't the actual data that you use alter for that. So this is one of those commands that has a variety of different uses that are honestly kind of different from each other. And I don't use this very often. So pretty much every time I need to do something like that, I look up the syntax for how to use alter because it's just not used super commonly. But yeah, that's how you do that. It's not insert. Good question.
All right. Thank you.
You're welcome. Any other questions before we take a quick break? Questions. All right, it's just a hair past 11:20. Let's take like a 9-minute break. Can we come back at 11:30? And I'm going to talk a little bit about installing and managing Postgres.